Ismail, take us away.
Thank you very much, Ben. Thank you, everyone, for the very warm welcome. It's great to be here at UBC. And it was working before we started. Okay, maybe. Yeah, there you go. Great. Yeah, so I'm Ismail, and I've just joined the Physics and Astronomy faculty. And today I thought of just giving a broad overview of scanning transmission electron microscopy, how we use it, how we prepare samples, and what kind of information we can get. I realized as I was making the talk that there's not enough time to cover kind of all the key aspects of microscopy. So hopefully this seminar, we'll have future seminars where we can delve deeper into different aspects of the technique. But as a teaser, so this is the kind of things that I like to do. I like to visualize order and disorder in quantum materials. This material here is strontium titanate. It's one of the most common substrates and materials used in condensed matter physics and quantum materials research. And I've spent the last few years developing cryogenic capabilities for the STEM because it turns out that it's quite difficult to get to cold temperatures without sacrificing resolution and stability. And we were able to visualize the kind of emergent order and disorder at low temperature in a so-called quantum paraelectric phase in this material. I will not talk about this today. There is a seminar at the end of February 27th, QMI, where I actually will delve deeper into the physics and science of this material. But for today, I really just want to give a broad overview of the technique of STEM, what it looks like, where you can find it, how you can use it, and so on. So my research broadly spans materials that we like to call quantum materials or strongly interacting or strongly correlated systems. As an example, this is the common perovskite structure, ABO3. You have the A sites here in green in the corner of a cube. On the center, you have the B site, so a transition metal typically. And then on the, and this transition metal is surrounded by octahedra of oxygen. And these materials have large chemical diversity and structural diversity. And as a result, it can host a variety of electronic phases. So unconventional superconductivity, ferroelectricity, multiferroic order, so various electronic and magnetic properties. And what I like to do is to understand how the structure impacts the electronic properties of these materials. As a simple example, so imagine you have a highly symmetric cubic structure of a material like a perovskite. If the atoms distort away from their high symmetry positions, that in turn gives rise to polarization, electric polarization, which is a useful property for ferroelectrics and ferroelectric RAM and so on and so forth. And my key technique is I use microscopes to visualize these atomic displacements as well as how they vary in space due to nanoscale fluctuations. Of course, the microscopes that I use don't look like the optical microscope in the cartoon, but this is a simplified diagram of the scanning transmission electron microscopy technique. So we start with an electron gun that generates electrons that are accelerated to high voltages. And then these electron beam is focused using electromagnetic lenses into a very fine sub-angstrom spot. So very fine spot that we scan across our sample. And the electrons transmit through our sample. And we can detect a variety of signals, both elastic and inelastic. And there's many, many different schemes depending on the quantities of interest. So if you go downstairs in Ampel, this is the microscope at UBC. So you can see in the bottom, we have the electron gun. There's a bunch of these modules. Those represent the electromagnetic lenses. Our samples go here in this black area through a sample holder. We have additional lenses for projecting the beam. And then detectors at the top to detect a variety of signals from elastic to inelastic and so on and so forth. And very soon, there will be another scanning transmission electron. I should have said, by the way, that this microscope is aberration-corrected, and I will get into that. And it's also monochromated, so we are able to generate an electron beam and then sort out the energy so that we have a very fine energy resolution, and that's useful for kind of future studies of collective behaviors in materials and electronic excitations. And very soon, next doors, there will be another microscope. This time it's a test scan tensor. It's a dedicated 4D STEM. I will discuss that a little bit later. And you can talk to Professor Ben Britton about the capabilities of this tool and how it can be complementary to the Nion next doors. Okay, so what's in this technique? So it's scanning transmission electron microscopy. One of the key terms is electrons. And so the wavelength of electrons, this is a plot showing the wavelength in lambda in angstroms as a function of the acceleration voltage or the energy, kinetic energy. And you can see that at 300 kilovolts or 200 kilovolts already, the wavelength of electrons is much, much finer than any typical bond length you will find in a material. So 2 picometers, whereas typical bond lengths are going to be in the order of 200 picometers. And from depending on the wavelength, if you follow just diffract and optics, the minimum resolvable feature scales with the wavelength and is inversely proportional to the convergence angle. Indeed, when folks realized that the electrons have this matter-wave duality, in 1930s, Ruska built the first electron microscope. And you can see that instantly there was an improvement in resolution relative to light optics. And as I said, you can resolve finer features if you reduce the wavelength by increasing the acceleration voltage. And this is, for many decades, what the story was. By increasing the acceleration voltage, you could achieve higher and higher resolution. And the hope was to break to this 1 angstrom regime, because 1 angstrom is kind of considered the minimum you need to resolve bond lengths in atomic structures. However, you'll note that this lambda is quite small, yet we're not able to resolve small features. And that's because in addition to the wavelength, it turns out the electromagnetic lenses, so these are round magnetic lenses that we use to focus the electrons and shape the electron beam, have aberrations. And in particular, spherical aberration, which in analogy to the bottom of a bottle, it kind of over-focuses electrons that are far from the optic axis. So you end up with a blurred image. So you actually are not able to reach the highest resolution because of these spherical aberrations. And so he took the development of aberration correctors. This is one prototype by Krivenek. This is a picture I took at Cambridge in one of their museums showing one of the first aberration correctors. And what that did is that now we can dial back our acceleration voltage, and we can use aberration correctors to break to this 1 angstrom limit. And then for now, a couple of decades, we've been able to reach sub-angstrom resolution in the scanning transmission electron microscopes. So this is a cartoon picture of silicon. So if you look at it from the 110 directions, it has these atoms that are about 136 picometers apart, 1.3 angstrom apart. And this is an image before correction. And next to it, now you can nicely resolve the silicon dumbbells, right? So the aberration correction was key to kind of break through that 1 angstrom limit and start resolving atomic structure with high resolution. So scanning transmission electron microscopy is not just one technique, it's actually a series of techniques. One of the most popular methods, and in fact, a lot of the images I'll show today are based on this technique, where we put an annular detector. So we collect electrons that have scattered between an inner angle and an outer angle, and we integrate the intensity over this kind of donut-shaped detector. So, and then we scan our electron beam across our sample. So for each scan position, we integrate the signal, and we get a number, right? And what's beautiful about this technique is that it has very nicely interpretable contrast. So if I take a crystal structure like this bismuth, strontium, calcium, manganite perovskite lattice, look at it from a high symmetry orientation, and take an image with a stem where I form this image by scanning across the sample, I get this really nice, nicely resolved image with bright dots representing the bismuth, strontium, calcium atomic column, and then I have these darker dots representing the manganese. And that's because in this imaging mode, my contrast, my intensity scales with the atomic number. So heavier elements will scatter more to higher angles, so I get more signal. The lighter elements will scatter less, so I get a weaker signal. And you'll note that the oxygen atoms are not visible in this image. That's just because the cross-section is too small in this particular imaging mode. You can also do spectroscopy. So you can also collect so the electrons, as it travels through the sample, it will interact inelastically with the material and lose energy. And you can then disperse the electron beam with a magnetic prism. And this is quite useful for chemical identification, for instance. So this here is a heterostructure. This was grown with molecular beam epitaxy. And it's a lanthanum strontium manganese oxide material alternating with strontium titanate. And you can see if I look at the spectra coming from the region containing the manganese oxide sample, you can see I get a nice signal here representing the lanthanum edge, and it's missing in the region, in the layers that don't have lanthanum. And you can see we have manganese, which is much weaker in the strontium titanate layers. And inversely, with the strontium titanate, we get a strong titanium edge, and that's missing in the manganese oxide layer. So this is very useful for chemical identification at the atomic scale. And you can go even further. So it turns out that the shape of the spectra and their energies can uniquely fingerprint the oxidation state, the valence state, and charge transfer. So this is very hard to see, unfortunately. But if you actually, we have the line cuts here. So in both cases here, the green and the red are a europium signal. But you can see here that at the interface between this europium titanate and this dysprosium scandate, we have this single layer of europium 3+, whereas most of the materials grown on top is europium 2+. So this shows you an example of how we can map charge transfer at the atomic scale. Now, with these electron energy loss techniques, I should also say, and I apologize for this, so now I flipped the diagram. So until UBC, all my microscopes had the gun on top. So usually I thought of the electron beams going down. The first diagram I showed you was going up. So just keep that in mind. But this is the same diagram, just flipped. But for EELs, typically the electrons coming out of the gun will have an energy distribution of about 300 milli electron volts up to 1 eV, at 1,000 milli electron volts, which is sufficient for mapping this sort of core loss excitations in materials that can do chemical mapping. However, so here at UBC, we have a microscope that now also has monochromated capabilities, meaning we can sort the electron beam and finally and create a fine electron beam in terms of energy resolution. And so this is data taken downstairs with about 7 milli electron volt energy resolution. And in contrast, if you think of 300 milli electron volt, that's much wider than this plot over here. This is data taken by Tian Xiao or Tony in Ziliang's group. And you can see, for instance, how we can start resolving features that were previously invisible in EELs because of this ability to go to ultra-high energy resolution and resolve fine changes in the energy loss with milli-electron volt level resolution. So I want to transition now to kind of a workflow, how we prepare samples and some of the limitations and capabilities of STEM. So it's in the name, so transmission. So in this technique, these electrons have to go through our sample and collected after the specimen. And so our samples are typically have to be thin so that the electrons can go through them. So normally we operate in a regime between 20 kilovolt to 300 kilovolt acceleration voltage, and the electrons have to go through our sample. And as I've said, they have to be thin, and typically we work up to 100 nanometer thickness for samples. For historical reasons, we put these samples on these 3 millimeter grids, which go on a holder and inside of the electron microscope. And the holder and the sample go in the middle of the electron microscope column. So the simplest method, you can just grind a sample that you have. And if you grind it finely enough, the edges of the grains might have thin regions that can be imaged. But of course, this has no control over orientation. And it's a rather crude method, but it can get you at least, if you're curious about some aspects of your sample, this is a quick and easy method to prepare your samples. In some cases, you might be looking at things that are already small, so nanoparticles or colloidal nanoparticles that are in some sort of solution. And in this case, all you have to do is drop cast. So you deposit a small amount of liquid or solution and let it dry up, and then you end up with small, thin samples. Getting a little bit more involved is mechanical polishing, and you can find mechanical polishers throughout UBC and including here in this building. And in this method, we glue our specimen onto this post, and then we angle it at a few degrees. And as you polish, you end up in the very edge of this kind of sample with very thin regions that are electron transparent, and you can image through them using the electron microscope. Okay, now getting even fancier, as we can use focus ion beams. So a focus ion beam is essentially a scanning electron microscope with an electron beam that scans across a sample, and then angled to it is a different ion column, a different column that uses ions. And we can use the ion beam to both image the material and to kind of remove material. And so what we do is we can dig out trenches around your crystal or your sample. We can lift it out and then thin it to electron transparency. This method is nice because it's size selective. You can find a specific region of your sample. Say there's a grain boundary that you want to look at or some sort of interesting features. You can go right there and lift it off. It's flexible and it can be applied to a variety of materials. And you can find different focus ion beam columns throughout UBC. I'm just highlighting some of these, and we'll try to have this information out so that soon, so that you can have a sense of where to prepare samples using focus ion beams. So this is one example of how you can use it for site selective lift out. This here was a device used for spintronic applications, and this device comprises this 2D material tantalum ditelluride. It's exfoliated on silicon, and there's multiple layers deposited on top. So we were able to go to the active area, lift out this sample, and image the orientation of this tantalum ditelluride. And you can see the individual layers of the permalloy, the aluminum oxide, and far, far above, there's a silicon oxide. So this is some of the capabilities of focus ion beam for orienting crystals along specific directions for imaging. Another technique, which is probably of interest to people here, is 2D materials. So 2D materials are these layered materials that can be exfoliated using Scotch tape. So this is a picture showing exfoliation of a 2D material. And then you can align thin flakes and transfer them on specific locations on your grid. This is one example where we've transferred a 2D material over a silicon nitride with holes, and we typically image through the holes. So we have a very thin specimen. And this is one example of looking at a material suspended over a hole, and this is the STEM image that we acquire of that particular material. And this is by no means exhaustive list of sample preparation techniques. Anything that can get you thin enough would work. So there's other methods that I don't have experience with, but that are available, including dimpling, ultramicrotome, electropolishing, and so on and so forth. So a lot of other techniques. But the key takeaways is that for STEM, we need to be able to go through our sample. So it has to be thin, and there's multiple ways to get there. Okay, so next up, I wanted to just go a little bit over some basic data analysis we typically do with our images, at least in my research. So as I've said, this is a diagram of the STEM. We scan an electron beam across our sample. We detect signal at each scan position, and we can form an image. This here is strontium titanate crystal. So this image, if you think about it, is essentially made up of multiple Fourier components. So it encodes multiple periodicities. And if we take a Fourier transform of this image, we get a Fourier transform. And if we take the amplitude, we can see now we have these spots that corresponds to the dominant frequencies in your image, right? And so in this case, these dominant frequencies are the lattice periodicities in your crystal. What's really nice about having a real space image to start with is that this actual quantity here is complex. We typically plot the amplitude, but we can always go back and do an inverse Fourier transform to recover the image because we have both the amplitude and the phase. Some basic analysis one can do is you can apply filters, for instance, on a particular periodicity, let's say on the 100. If you inverse Fourier transform that, you end up with this kind of essentially a 2D sine wave that encodes the periodicity in this image. And in this case, it's not very interesting. It just tells you we have a strongly periodic structure in this material. We can do this in other directions, and you get the sine wave now oriented along a different Fourier direction. So other things we can do is that if we now look at this argument of this function here, so of the Fourier components, so it's a dot product between the particular periodicity or the wave vector that we're interested in with the position, and then we also add a phase term. Now, in the case of an ideal structure with no defects, no variations, this phase term is constant, and you get essentially something that looks like this. It's just a perfect sine wave. There's nothing interesting. However, if you have imperfections in your crystal, if there is local variations in the material, then that phase will not be constant, and we can even then take the phase and take the gradient of the phase and start mapping local strain in the material. And this will become useful, for instance, when you have an imperfection in the crystal. This is lanthanum calcium manganite material, and you can see that we have a nice periodic structure, but in the middle of this image, we have a dislocation. So this is an edge dislocation in the crystal, and if we extract the phase, we can see that it winds around that core of the defect as predicted. And then if you take the gradient along the different directions, you can map, and unfortunately it does not look good on the projector, but there is a positive and negative, there's localized strain at this dislocation. And you can also use this to visualize more complex defects. So in this case, these are stacking faults in the crystal. The crystal did not grow perfectly, and so then there is a phase shift between or a half unit cell shift between different parts of the sample, and those phase shifts can be visualized through these pi phase slips in the crystal, right? So these are defects that you can see by eye, but this is one way by using Fourier transforms you can extract these spatial variations in the image. So now I'd like to get into a little bit more kind of advanced methods of extracting more subtle phenomena in these images. And in particular, as I said at the intro, I'm interested in how atomic displacements are tied to electronic properties in complex materials. So for instance, if I have a material where the atoms shift up and down or modulate in space, that can be tied, for instance, to charge order. This is one example of how we mapped charge order displacements. So these are atomic movements, or atomic displacements, when the materials enters a so-called charge ordered phase. And you can see that what I'm showing here are arrows representing the direction and amplitude of the distortions of individual atoms in this material. Yeah, and in terms of the atomic displacements, there's a variety of complex displacement modes. So one example are these ferroelectric type displacements, where when the atoms move away from the center, they break inversion symmetry. Other examples are these octahedral rotations in oxides, and these mediate metal insulator transitions and enter ferromagnetism. So what we typically do is we use electron microscopes to visualize these atomic displacements and try to understand the role they play in the macroscopic properties. So what I want to show you next is that, even though our resolution, so obviously we have resolution below 1 angstrom, so we are able to resolve distances less than 1 angstrom. Typically, we can reach 50 picometers, so that's 0.5 angstrom. However, we can also detect the centers of the atoms over the atomic columns with precision that is much higher than the imaging resolution. So typically, if we model our images with some sort of 2D function, typically a Gaussian, and we fit the centers, we're able to localize these blurred images of atoms with picometer level precision. And that's kind of a length scale that is smaller than typical atomic displacements in many of these complex oxide materials. So the first thing we have to solve is that, being a scanning technique, as a reminder, we're scanning our electron beam across our sample. So what we typically do is we go from the left to the right, and we jump back to the beginning. And so we can define there's a really fast scan direction, And then there's a slow scan direction. So between here and here is quite fast, but then between here and here takes some time. And so being a scanning technique, it's very susceptible and sensitive to these to any movement of your sample or any vibration, any shift in your specimen. And typically these shifts will come from temperature changes, from acoustic noise or mechanical noise. And this is one example of looking at strontium titanate. And if you scan very slowly, so 20 microseconds per pixel, this whole frame takes about 20 seconds. You can see now that my image is quite distorted, and it's kind of less useful for quantification. Now, if I can go really fast, if I can take a really fast scan by dialing back my acquisition time, so 1 microsecond per pixel, that same image can be acquired with in less than a second or about a second. And now you can see that there's less distortions in the atomic, in the lattice, like in the lattice arrangement, right? So these things are more 90 degrees now, and it's much less distorted. However, it comes at the expense of signal to noise ratio. You can see if you zoom in that there's more noise in individual columns. So what we do then is we use a technique that is fairly well known, which is image alignment. Your phone does that when you take multiple scans, then it aligns images so you have a higher signal to noise image. This is a single frame. This is about 20 frames. You can see now that the signal to noise ratio is much, much higher. And which means we can start quantifying these atomic positions with much higher precision. Whereas here, the precision would suffer greatly, and therefore you're not able to map picometer scale distortions in the atomic lattice. Okay, so then we can take our images, and what we're going to do is we're going to model this image as a sum of two-dimensional Gaussians. And then from that, we can find the centers of the atomic column, and we can verify that our residuals, so that our model image represents the data, and we've found the centers of each atomic column in this material. So next up is we can begin to quantify what the precision of this exercise is. So we can look at the distribution of bond distances in the material. Strontium titanate at room temperature is expected to be cubic. And so by plotting a histogram, we can find that there's a distribution of about 3 picometers and 3 picometer precision. So it means we can quantify our atomic distortions with this level of precision. And if you have even higher signal to noise ratio, or if your conditions are better, you can even push to the 1 picometer scale. So why do we care about 1 picometer? Because it turns out a lot of these atomic displacements are in that scale. So charge order, ferroelectricity, oxygen octahedral rotations range from anywhere between 2 picometers to 20 or even 30 picometers. So having the precision enables us to map these atomic displacements and visualize their behavior. So as an example of what you can do with this, so where's the, okay, so this material here is this quadruple perovskite. That's what we call it. It's a bismuth copper manganese oxide. So we can find the atomic positions for each of these atomic columns. And one of the simplest things we can measure is just the lattice constants along the y direction and the x direction. We can say, what is the size of the unit cell along y versus x, right? And so when we do this, here is a plot over a large field of view. Each pixel here represents a unit cell. And you can see that in this image, we have these sort of stripes that form in the material. And these indicate that there is domains, ferroelastic domains that emerge in this system. And we did this by measuring here the lattice constant along the x direction. We can also do the same thing along the x direction. You can also map rotation, monoclinic distortion, and so on and so forth. So you can really get to unit cell by unit cell into the details of the atomic structure. Other more functional things you can measure are ferroelectric displacements. So in a ferroelectric material, the atoms in the center shift away from the center. So they break inversion symmetry and they create an electric dipole. And these ferroelectric materials can be switched with an electric field. And so they're useful for ferroelectric memory and for electro-optic applications. I'll get into that in a little bit. And what we can do here is we can, again, find the center of each atom. We find the center of this central atom, and we compare its position relative to the center of mass of these blue atoms. And by doing so, we find that it's actually not sitting in the center, but it's displaced away from the centrosymmetric position. And we can do this for each unit cell, and we're able to map the polar displacements. In this case, this is barium titanate, a well-known ferroelectric material. And as a kind of an example of how this is useful, so barium titanate is being explored, including here at UBC, as a material for electro-optical applications. So essentially, ferroelectric materials have these nonlinear dielectric functions that can be used for tuning the index of refraction of devices and then guiding light. So it's very a promising candidate for that purpose. They typically want to grow it as a thin film to be integrated into a device. However, it turns out that in the growth of these materials, there's often defects. Some of them you can see by eye. So these are crystalline defects. So these are imperfections in the atomic lattice. These are examples of dislocations like we saw before. But on top of that, we also need this ferroelectric or polarization to be pointing in one direction. And having multiple domains could be problematic for the performance of these materials. And so what we can do then is we can map the displacements of the titanium atom in barium titanate, and we're going to color the displacement by the angle of displacements, which would tell us something about the orientation of the domains. So this is one example of barium titanate grown in stoichiometric conditions. So equal amount of barium, equal amount of titanium. And while the structure looks okay, when we map the polarization, we find that we actually have both domains pointing up and down. So the domains are not uniform, and there's kind of tens of nanometers fluctuations, or over length scales of tens of nanometers, there's variations in the polarization direction. So one option is you can grow a titanium-rich condition, so more titanium than barium. It actually gets even worse, where we have more smaller domains, and there's more of them over the same field of view. And then finally, in this work, this was led by Ashley and Rob Westervelt's group at Harvard and Julia Mundi. So they grew this barium-rich sample, and in that case, well, we did see some crystalline defects. The polarization overall tended to point along a single direction. So this is just one example of how we could use STEM, mostly here in this case for metrology applications and figuring out how order emerges in these systems. Okay, how am I doing with time? Okay, so far I've focused on STEM, an ADF STEM. So it's just one imaging technique within the broad suite of techniques you can perform in the microscope. So as a reminder, we scan our beam across the sample, and we integrate the signal over this kind of ring shape for each scan position. So we end up with one number, intensity, per scan position. So it's a 2D image at the end. Now, more recently, over the last 10 years or so, there's been a huge boom in these pixelated detectors. So rather than put in just one detector to collect only a small slice of scattered electrons and throwing out the rest, we're able to now collect the full diffraction pattern, the fully scattered electron distribution on a pixelated detector, on a two-dimensional detector. And these detectors had to be fast, with high dynamic range, because they need to be able to collect the unscattered beam, which is most of the signal, and the weaker spots that scatter to higher angles. And you need to be low noise. And this has been growing as a technique. It's available on both microscopes here at UBC. You can perform these sort of measurements. This is one example of how it can be used to determine grain orientations or crystalline structures. And it's known as 4D STEM. So 4D, four-dimensional pattern. I forgot. I'm being recorded, so I will not comment on the name. But but it's known as 4D STEM. It's also known as scanning nanobeam diffraction. It has a lot of other techniques, other names. And in particular, the tensor here, you can talk to Ben, Professor Ben Britton. And it's really designed for these sort of measurements, but we can also perform this on the neon microscope. So this is one example of a diffraction pattern taken by my group. And from these, so now I have this diffraction pattern for each scan position, and now I can begin to reconstruct new imaging modes ad hoc, so after the fact. So I can integrate, I can take differential differences, and in this case, I'm just integrating a ring to form a virtual dark field image, but I can also measure the space in between the diffraction spots and map the strain. And what's really exciting about this method is now, look at the scale bar. We're a 15 nanometer scale bar. So this is about a 200 to 250 nanometer field of view. Previously, with the ADF stem, I had to have a really nice image of each atom. And because of the sampling requirements, you were limited to fields of view of about 50 nanometers to maybe 70 nanometers tops. So now we can extract similar information with much higher signal to noise ratio, because we're collecting every electron. We're not throwing away most of them. And we can collect over much larger scales and kind of discover and access mesoscale order in materials. So things that happen on the tens of nanometers rather than the few nanometer scales. And this is, again, very powerful. I won't get into the details here, but this was used to, for instance, map novel polarization textures, these swirls of polarization in oxide heterostructures. And in a month or so, when I present the seminar on quantum parallax strontium titanate, we'll get into this in more detail and see how we used it with low temperatures to access new phases. So I want to kind of wrap up with kind of a quick discussion about in situ and cryogenic capabilities and the challenges. So as a reminder, we typically make a sample, 3 millimeter grid. We put it on a sample holder, and this thing is inserted in this goniometer. And there's a lot of restrictions of the size and dimensions. For one, our sample has to fit in this pole piece. This is the objective lens. You have about 3 to 5 millimeters of space. And moreover, the diameters of these rods limit you to a few millimeters in inner bore. And so introducing cooling, biasing gas becomes extremely challenging. And as a result, cryogenic capabilities in the STEM have historically lacked compared to the capabilities of the microscope. And so what I've spent a lot of time on over the last few years is developing cryogenic capabilities. This is an example of a commercial liquid nitrogen holder. This will get you to about 120 Kelvin. Even though liquid nitrogen boils at 77 Kelvin, there's a lot of thermal losses by the time you reach your sample. So this introduces vibrations. As the cryogen evaporates, it's shaking, it's mechanically vibrating, it's acoustically making noise. Temperature is changing over small time scales. And so then you have sample motion and all of the issues that I pointed to at room temperature that we needed to optimize are significantly worse at low temperatures. And to fully harness the kind of capabilities of especially the Nion microscope, so we've developed in my group this kind of new kind of sample holders where we now use a continuous flow from a much larger external dewar. And as the liquid helium flows, and it cools a heat exchanger, which is thermally coupled to the specimen, we reach temperatures of about 20 Kelvin. And we can vary temperature between 20 Kelvin to room temperature with high stability. And moreover, we can maintain any temperature between that range for hours on end. And so I think this will be very useful for collecting some of the weak signals we're interested in collecting in the microscope downstairs. And in particular, a lot of these quantum materials, they have this pesky feature that a lot of the interest in physics happens at low temperature. So we need to be able to access those low temperatures. You'll notice there's this thing in the middle. This is flexible bellows with viscoelastic spacers that help damp vibrations introduced by the mechanical connection to the transfer line. But we've demonstrated atomic stability, sub-angstrom STEM, as well as TEM. And the stability and drift are low enough that we can perform the same kind of measurements that I showed at room temperature at lower temperatures. And so, again, my hope today was just to overview the techniques. I'd love to, obviously, meet with whoever is interested to discuss more details on the science and some of the problems we can tackle. These are the people that were involved in the things that I showed today. I especially want to highlight a lot of the legwork was done in my previous advisor, Lena Krokuris, and I've worked very closely with Berit Guj, who's going to be at Cornell very soon. My postdocs at the Roland Institute, Sakyan and Yang, led a lot of the development for the liquid helium, as well as this was done in partnership with Robert Hovden at the University of Michigan, with his student Nishkash Agarwal and Maya Gates. And I've had a lot of fruitful collaborations with Julia Mundy and Sangwook